What makes your smartphone so smart? The answer is semiconductors, the tiny engines powering our digital world. From your laptop's processor to solar panels, semiconductors control electricity and are the building blocks of modern electronics. They're not quite conductors, not quite insulators. Their in-between nature is their superpower. We can tweak and control them to create complex components like transistors and diodes. This ability to precisely manage electricity is what drives all our devices. Today, we'll pull back the curtain on the science of semiconductors and see how they've reshaped civilization. Let's dive in. To truly understand the magic behind semiconductors, the building blocks of modern electronics, we need to delve into the fascinating world of quantum physics. It might sound intimidating, but we'll break it down step by step. Semiconductors aren't just materials. They're carefully engineered landscapes where electrons play a crucial role. At the heart of it all, we need to talk about electrons. These subatomic particles are the key players in electrical conductivity. Their behavior dictates whether a material will conduct electricity, block it, or, most interestingly, do something in between. Electrons are tiny, negatively charged particles that orbit the nucleus of atoms. They're not just randomly floating around, they exist in specific energy levels, almost like orbiting planets around a star. These energy levels are crucial to understanding how materials behave electrically. When atoms come together to form solids, these individual energy levels merge into what we call energy bands. Think of it as a group of individual orbits blending into broader pathways. These energy bands dictate the allowed energy states for electrons within the solid material. To visualize this, imagine an apartment building. Each floor represents a different energy level available to the electrons. The valence band is like the ground floor, where electrons are tightly bound to their atoms, comfortably residing in their apartments. These electrons are not free to move around and contribute to electrical current. They're part of the structural integrity of the material. The conduction band, on the other hand, is the rooftop party, a place where electrons are free to roam and mingle. These are the electrons that can conduct electricity. For an electron to conduct electricity, it needs to get enough energy to jump up to the conduction band and move freely through the material. This jump requires energy, and the amount of energy needed is crucial. The gap between these bands, the valence band and the conduction band, is called the band gap. It's a region where electrons are forbidden from existing. Think of the band gap like a staircase between floors. The size of this staircase determines how easily electrons can move to the conduction band. If the gap is small, like a short staircase, electrons can jump easily with just a little bit of energy. This is characteristic of conductors. But if the gap is huge, like a massive wall, they're stuck in the valence band. This is what happens in insulators. Conductors like copper have overlapping bands, meaning there's virtually no gap. Electrons move freely and effortlessly, allowing electricity to flow with ease. Insulators, such as rubber, have a massive band gap, effectively trapping electrons in the valence band and preventing electrical current. Semiconductors, like silicon, have a band gap that's just right. Not too big, not too small. It's a Goldilocks zone for electrical conductivity. This just right gap allows us to control when electrons move to the conduction band, turning the material into a conductor or an insulator on demand. This control is the foundation of all modern electronics. This band gap, this seemingly simple property, is the key to a material's electrical behavior and its ability to be used in electronic devices. It's what makes semiconductors so special and so incredibly useful in everything from smartphones to supercomputers. Understanding the electron dance floor is the first step to understanding the digital world. Now let's break down the fascinating world of materials and how they behave in electronics. Understanding these fundamental properties is key to grasping how electronic devices function. We'll be focusing on the three primary categories that dictate the flow of electricity. The three main types of materials in electronics. These categories are conductors, insulators, and semiconductors. Each possesses unique characteristics that determine its role in a circuit. We'll explore their atomic structures and how these structures influence their electrical behavior. Conductors, like copper, are the workhorses of electrical circuits. They allow electricity to flow freely with minimal resistance. Have overlapping bands, specifically the valence and conduction bands. This overlap is crucial because it means there's no energy barrier for electrons to overcome. Electrons move easily, almost effortlessly, through the material's atomic structure. Think of it like a wide-open highway for electrons, making them great for carrying current over long distances and within intricate circuits. Copper's excellent conductivity makes it ideal for wiring and circuit boards. Insulators like rubber, on the other hand, are designed to block the flow of electricity. They act as barriers, preventing current from escaping where it shouldn't. Have a huge band gap, a significant energy difference between the valence and conduction bands. Electrons are trapped in their valence bands, unable to gain enough energy to jump to the conduction band and move freely, so no current flows. This makes them essential for safety and preventing short circuits. Semiconductors like silicon are where things get really interesting. They offer a middle ground between conductors and insulators, are in the middle, exhibiting properties of both conductors and insulators depending on external conditions. Their small band gap, compared to insulators, is the key to their unique behavior. Means a little energy, such as heat or light, can be enough to excite electrons. Let some electrons jump to the conduction band, allowing a small current to flow. This lets us control the conductivity of the material with incredible precision, whether they act more like insulators or conductors, simply by manipulating external factors like voltage or temperature. That's the secret behind transistors, the ability to switch between conducting and insulating states, the building blocks of computers and virtually all modern electronics. By switching conductivity on and off, rapidly and precisely, we create the ones and zeros, the fundamental language of computers, of digital logic, which allows us to perform complex calculations and operations. Semiconductors are the ultimate switchable material, enabling the digital revolution. It's all about controlling that jump of electrons across the band gap, and that control is what powers our modern world. Let's delve into the fascinating world of pure or intrinsic semiconductors. These materials form the foundation of modern electronics, and understanding their behavior is crucial to grasping how transistors, diodes, and integrated circuits work. We'll start by examining their fundamental properties and how they conduct electricity under different conditions. We'll begin with a look at a prime example: pure silicon. Silicon is the most commonly used semiconductor material due to its abundance and favorable electronic properties. Its atomic structure and how it forms bonds with other silicon atoms are key to its semiconducting behavior. Each silicon atom, in its pure form, bonds covalently with 4 of its neighbors. This creates a highly ordered, three-dimensional structure known as a crystal lattice. These covalent bonds are strong and hold the atoms tightly together. This bonding arrangement results in a stable crystal lattice, where each atom is held firmly in place. This stability is crucial for the material's behavior at low temperatures. The regular arrangement of atoms also influences how electrons move within the material. At absolute zero, the coldest possible temperature, all the electrons in the silicon crystal are locked tightly within the covalent bonds, residing in what's called the valence band. They don't have enough energy to move freely. Because all electrons are bound, there are no free charge carriers available to conduct electricity. Consequently, at absolute zero, pure silicon acts as an insulator, and no current flows through it. However, the situation changes dramatically as we raise the temperature to something more familiar, like room temperature. At room temperature, the increased heat provides some electrons with enough thermal energy. This energy can be enough to overcome the binding energy of the covalent bond. This allows them to break free and jump to a higher energy level, known as the conduction band. Once in the conduction band, these electrons are free to move throughout the crystal lattice. When an electron gains enough energy and jumps to the conduction band, it becomes a free electron, able to move and contribute to electrical current. Importantly, when an electron jumps to the conduction band, it leaves behind an empty space in the valence band. This empty space is called a hole, and it effectively acts as a positive charge carrier. So now we have 2 types of charge carriers: free electrons in the conduction band and holes in the valence band. Both of these can move through the material under the influence of an electric field, effectively carrying current. This entire process, where heat generates electron-hole pairs, is known as thermal generation. It's the fundamental mechanism by which intrinsic semiconductors become conductive at room temperature. Therefore, in intrinsic semiconductors, which are pure and undoped, the thermal generation process dictates that electrons and holes are always created in equal numbers. This balance is a key characteristic of intrinsic semiconductors. This gives rise to two distinct types of charge carriers within the material, each contributing to the overall electrical conductivity. It's a testament to the unique properties of silicon and other semiconductors that such complex behavior arises from such a seemingly simple, pure material. Pure semiconductors don't conduct well, so we dope them, add tiny amounts of impurities. Doping is like adding spice to a recipe. It changes everything. Add a group 5 element, like phosphorus, with 5 valence electrons, or a group 3 element, like boron, with 3. Even a tiny amount of these impurities transforms the material's conductivity. Doping creates extrinsic semiconductors, with either extra electrons or extra holes. This imbalance lets us design materials with specific electrical properties. N-type and P-type semiconductors are the foundation of all modern electronics. Doping is the secret sauce of the digital age. Doping silicon with phosphorus, group 5, adds extra electrons. 4 electrons bond with neighbors. The 5th is loosely attached and easily freed. These donor atoms create a flood of free electrons. N-type, negative, semiconductors. Free electrons are the majority carriers. Holes are few and far between. By adjusting the amount of phosphorus, we control conductivity precisely. This atomic-level design is what makes modern electronics possible. N-type materials are engineered for performance. That's the power of controlled doping. Now let's create P-type semiconductors by adding boron, group 3. Boron forms 3 bonds, leaving a hole, a missing electron. These acceptor atoms create lots of mobile, positively charged holes. In P-type material, holes are the majority carriers. Electrons are rare. The movement of holes carries most of the current. By controlling boron concentration, we fine-tune conductivity. The real magic happens when N-type and P-type materials meet, forming a PN junction. This junction is the heart of diodes, transistors, and integrated circuits. 2 types, endless possibilities. In semiconductors, moving charges, electrons, and holes are called charge carriers. Carrier concentration is how many carriers exist in a given volume. In pure silicon, temperature sets the balance equal numbers of electrons and holes, but not many. Doping changes everything. N-type has lots of electrons, few holes. P-type has lots of holes, few electrons. Recombination reduces the minority carrier numbers even further. By controlling doping, engineers create regions with different carrier concentrations on a single chip. This precision lets us build complex circuits and devices. It's the ultimate tool for designing the digital world. Semiconductors are the foundation of modern technology. By mastering band gaps and doping, we've built everything from smartphones to supercomputers. Billions of transistors, tiny switches, work together in every device you use. PN junctions make logic, memory, and amplification possible. The future, new materials, quantum devices, and even more powerful chips. Medicine, energy, AI, all will depend on next-generation semiconductors. Understanding these basics is the first step to inventing tomorrow. Next time you use your phone, remember the science inside. The world runs on semiconductors, and that's seriously cool.